So we have a half a mole of an ideal gas taken through the process on the PV graph to the right. First, we're going to find the temperature at each state. So we will use PV is equal to nRT, rearrange it to solve for T, and then substitute in all the information at A. So 4 times 10 to the 5th times 0.01 meters cubed divided by 0.5 moles times 8.31 joules over moles times Kelvin. All right, when we calculate that out, we get 962 Kelvin as our temperature at A. All right, to go from A to B, I'm going to use ratios here instead of calculating each one. So we have pressure and volume at A over the temperature at A equals the pressure and the volume at B over the temperature at B. So looking at this ratio, we start out with reducing our pressure by half. So if that goes down by a factor of 2 and the volume doubles, okay, we are going to find out that our temperature at B is going to be the same at A because those ratios stay the same. All right, now looking at C. So here, from B to C, we see that the pressure remains the same and that the volume increases to 0.3 divided by the temperature at C. So what will happen here is the temperature at C will be 1.5 times greater the temperature at B. So when we look at this, the temperature at C, 1.5 times 962 is going to be 1,444 degrees Kelvin. Okay, now we can actually put a little more detail on these diagrams. So we know that initially you have these particles at a certain temperature. It expands. The internal energy doesn't change much. All right, we'll get to that why later because the temperature doesn't change. And then as you go from B to C, the temperature increases, so the average velocity of the particles will also increase. Looking at our charts here, we know that from A to B, the temperature will not change and the pressure will decrease. So on here we have A to B, and then from B to C, the pressure will remain the same and the temperature will increase. So that is what our chart will look like for pressure versus temperature. For volume versus temperature, the volume of the object from the gas from A to B increases. So, and the temperature remains the same. So this will go up as the temperature holds constant. And then from B to C, both the volume and the temperature increase. So the line will go diagonally up. So now if we look at this here in terms of energies, the temperature remains the same from A to B. So the change in internal is 0. If we look at the work, the container expands, which means the environment, if it's pushing left on it and the container moves right, the work done will be negative. And since the change in temperature is the same, temperature doesn't change, delta U internal will be 0, therefore Q has to be positive. So going from B to C, again it expands, we're going to have a negative amount of work being done. Our internal energy is going to increase, therefore it has to undergo the heating process. So we have a positive Q in the last part. Now, as we go from A to B, to try to determine what the work done is, so we can figure out how much heating has occurred, we have to find the area underneath the curve, because this equation, negative P delta V, assumes a constant pressure, so it will not work. So we break this into two parts. We have the triangle and the rectangle. So the area here of the triangle is going to be 4 minus 2 times 10 to the 5th in terms of our change in pressure, multiplied by the base of that triangle, all right, which is 0.01 meters cubed. We're going to add to that the pressure from the rectangle at the bottom, and it's the same 0.02 minus 0.01 meters cubed change in volume. So when we look at this, because it is expanding, this whole value is going to be negative. So that triangle will give us negative 1,000 joules plus a negative 2,000 joules. So the work done here will be a negative 3,000 joules for process A to B. Okay. Now, since there's no change in temperature, we know that work plus Q equals change in internal energy. So we're going to have negative 3,000 joules plus Q is equal to 0, or Q will equal positive 3,000 joules. So as it expands and the pressure drop, it has to undergo the heating process to maintain the same temperature. Now, as we look from B to C, all right, if we look at this process here, since the pressure is constant, we can use our constant pressure work equation here. This will give us a negative 2 times 10 to the 5th pascals in pressure, times the change in volume, which is 0.03 minus 0.02. All right, so when we look at this, the work done here is going to be negative 2,000 joules, and that's from B to C. And then we will have to find the change in internal energy from B to C. So this is going to be 3/2 NR times 1,444 minus 962 Kelvin. And when we calculate all this out, we will get a positive 3,000 joules. So when we look at our conservation of energy for the process of B to C, we have work plus Q is equal to a change in internal energy. We have negative 2,000 joules plus Q is equal to a positive 3,000 joules. So during this time, in order for the temperature to increase and for it to expand, it has to undergo the heating process. 5,000 joules